Enough? Okay, you guys do the next one. You guys, oh, now hang on a second here. Next one's out of twist here, doesn't it? Okay, let's read this first, and then we'll do it together. A major metropolitan newspaper surveyed a simple random sample of 200 voters. They asked whether or not they planned on voting for a new bond act. 55% said that they planned to vote yes. Okay, now what we're really interested in here is they do surveys like this all the time. They do voter surveys all the time. What we're really interested in, we want to know what proportion of the voters are going to vote yes. All of the voters, right? We're interested really we're interested in the value P, right? Oops. Come on. We're interested in the value P. What's the proportion of this population that's going to vote yes on this bond act? Well, you ain't going to know that until the election, right? Before the election, the best you have is a sample. In this case, sample of 200 people. Okay, we're going to call that proportion. What do we call the mean of a sample before? Call it X bar, right? Let's call this P cap, right? Don't ask me why they use a cap instead of a bar. And just keep everything nice and neat and the same and stuff like that. We're going to call the sample proportion P cap. What's the sample proportion? What percentage of people voted yes? Yeah, it's equal to 0.55. Okay, so now, if I remember what my formula was for my confidence interval, it was X bar plus or minus the Z-score. The Z-score depends on whether it's, I want alpha equals 0.05, the level of error I'm willing to accept, 95% confidence interval, in which case it was 1.96. Don't worry about what I just said. It'll make sense to you in a week or two. 1.96 times the standard error. Okay, so X bar, it's pretty simple to make the analogy that P cap is kind of like X bar, right? But we need a standard error. So we need a formula to calculate standard error, right, that takes into account the size of the sample and the proportion. Well, as it happens, the standard error is equal to the square root of P times 1 minus P, actually P cap, times 1 minus P, because you don't know what P really is. It really is P, right? P times 1 minus P, the population proportion is really what we need here, but we don't know it. But since it's a sample of 200, a big sample, we're willing to use P cap to represent the population proportion, just like we do with the mean, over N. Bigger N is, the smaller standard error is. Same as before. Bigger the sample size is, the smaller the standard error is. Smaller the standard error is, the smaller the margin of error is, and the narrower is the confidence interval. Works exactly the same. So let's calculate this for this problem. Standard error is equal to the square root of 0.55. Now what's 1 minus P? 0.45, good. Over, sample size was 200. All it is under that square root sign. So let's calculate that. Clear, click clear, is going to be 0.55 times 0.45 divided by 200 is equal to 0.00123. Looks a little strange, but now we got to find the square root of it. Square root of it is 0.035. Square root of a decimal is a larger number. It makes it a bigger number. Because if you look at it as, if we multiplied 0.035 times 0.035, we would have got that number we originally started with. So it's 0.035. It's 3.5%. Our standard error is 3.5%. So now to find our confidence interval is going to be equal to P cap plus or minus, for a 95% confidence interval, okay, is going to be equal to P cap plus or minus 1.96 times our standard error. Okay, again, standard error is just a distribution of all those proportions. If we did it over and over again, a sample of 200 over and over again. Okay, so P cap is 0.55 rather, plus or minus 1.96 times, what was it again? It was 0.035. right? So let's figure this out. So it's 0.55 plus or minus, and let's work that out, okay, times 1.96, okay, is 0.06, 0.069, I'm going to call it. I'm going to round it off, 0.069, make it a little easier on myself, 0.069, 6.9%. That's our margin of error. Now, kind of makes sense now in a poll, right? Now we're talking about an election, a poll, and that's what they do with elections. They do a little something special we're going to learn later on, just to make things a little easier, makes things a little simpler for them to calculate when they're polling many different candidates, right? But if it was only a single thing like this, like a bond issue, they would use this. Case, yes.
I'm sorry, not to interrupt you. So if we say that margin of error, that's how we leave it on the answer, like on a test. We don't go.
No, we're going to calculate it. We're going to go ahead and calculate. So what's our 95% confidence interval? We're 95% certain that the true value of P for all the voters, in other words, the outcome of the election, we're 95% that the true value of P is going to be equal to 0.55 minus 0.069, which is going to be 0.481, right? 2.619. Okay, yeah, I'll take your word for it. Okay, are we sure that this is going to pass? No, we're not sure, right? Because it could, this within the range. Are we 95% certain this is going to pass? We're not, because it is possible, it is within our 95% confidence interval that less than 50% of the people are really, that the real population proportion is 50%. We have to be a little bit careful with this, right? It's easy to say, here's my confidence interval between here and here. I'm going to compare it to something else which turns out to be out here, or something else that turns out to be in here, to see if it's within my confidence or outside of my confidence interval. We got to remember something, though. The way that this really works is that if we know what the real P is, what the real population proportion is, we can use this to predict what 95% of the samples of a certain size would be, what range they would be in. That's really what we're doing. That's really what this math is doing for us. We're using it a little bit differently here, but I got to be careful about using it to predict stuff. We got other tests we're going to use later on, like the t-test and stuff like that. But now we really maybe should, for the time being, stick to just using it in our heads as something that predicts whether or not we captured the true proportion. Okay? But in something like this, in an election, they would use this to predict whether or not they thought that they're 95% certain that this bond act would pass, for instance. So they might actually use this in this manner. Okay. What's the margin of error for this poll? What was the margin of error? Margin of error was that 0.069, right, that we're adding and subtracting. Just to let you know, I might as well bring this up now. Okay. In real polls, what they'll frequently do is they will ask voters who you're voting for. Voting for Hillary. I'm voting for Kerry. I'm voting for, and so on. If you have a number of candidates, let's say there's actually going to be a real Democratic runoff this year for Democratic primaries, and there's actually some competition. We'll make believe, right? So let's say like so many people say they're going to vote for Hillary, so many for Kerry, so many people for whoever else. Who else might possibly be running? Biden. Yeah, Biden might be running, right? So Biden. So you have a number of different candidates, right? And certain proportion might vote for one, certain proportion might. And if you can imagine, if you calculated the standard error for each one of them, the margin of error for each one of them would be different, because it's point P times 1 minus P over the sample. Even if the sample size is the same, P, if Hillary has 49% of the vote, P is 0.49 times 0.51. If Biden has 10% of the vote, then standard error for Biden is 0.1 times 0.9 over n, square root of that. It's going to be different margins of error for everyone. You never see that in a poll. What they do in a poll is they take the worst case. The biggest number you can get for square root of P times 1 minus P over n is if P is 5.5. So they ignore what the proportion is for each individual and say 0.5 times 0.5 over the sample size. Take the square root of that, and that's the standard error for everybody. They don't individually calculate standard errors. That's why they can say, oh, we think Hillary is, like 39%, and Biden is 10%, and this person is 11%, plus or minus 3% for everybody, right? Where if you really have to do the math, well, gee, maybe that margin of error should be different for each one of them because the proportion is different for each one of them. But I don't want to deal with that, right? Because in fact, most of these polls are nonsense anyway. So nobody ever votes the way they actually tell somebody that they're going to vote anyway. Okay, so let's apply this to a real world situation, something in public health that's occurring right now that's a real problem. Okay, let's see. All right, so now you may have noticed that there is a proliferation of of zombies around, right? Zombies on TV, zombies in the movies, zombies in schools, it's everywhere, right? So we're going to use our confidence interval now to calculate a few things about zombies. Primary food, there's a zombie food pyramid, by the way, right? You're all the way up to the top, like bones and gristle, gnaw sparingly, So at any rate, the primary food source is brains and spinal cord diet, high in protein, low in carbohydrates, form of a low carb diet, right? Serum cholesterol levels are measured in 25 randomly selected adult zombies. I got a problem here, don't I? 25, it's a small sample size, right? I can't use a sample size of 25 for my standard deviation, so I'm hoping I'll get more information. The mean of the sample is found to be X bar is equal to 151.4. That's the total cholesterol. The population standard deviation, sigma, for zombies is assumed to be the same as for living humans, 38 milligrams per deciliter. Okay, so they gave us the population standard deviation. Fortunately, since it's a small sample. Even though it's a small sample, we can calculate our confidence interval now because we know the population standard deviation. If we didn't know the population standard deviation, we would have a problem with a sample smaller than 30. We couldn't depend on the sample to give us a reliable standard deviation for the population. Okay, so let's calculate this. Find the standard error for zombie cholesterol. Okay, I'll leave that up to you guys. Okay, sigma is equal to 38, sample size is 25. I'll pull up a piece of paper in the meantime. Let's see how you guys are doing online. Okay, you guys online seem to be doing pretty good too.
Hey, Tony?
Yes. Keep an eye out the window for those zombies, though. If you hear any banging on the doors or anything like that. Yes.
Not to sound redundant again, just to repeat again.
Sure.
Because that n equals 25, we're going by the basis of n equals 30 or something.
Oh, no. We're using n equals 25, but since the sample size is so small, we could not use the sample to figure out what the standard deviation is. Right. See, fortunately, they told us the population standard deviation is 38, right? So we're going to use 38. If they hadn't told us that, we couldn't, based on what we know now, we couldn't do this problem. Okay. Because I would not be able to depend on the population standard. Based on what we know now, right. Okay. I wouldn't be able to depend on the sample to give me the standard deviation of the population or give me a decent estimate of it. But they told me it was 38, so I don't have to worry. Now I can do it for any sample size I want. As the sample size gets smaller, my confidence interval is going to get ridiculously wide, right? Because that standard error is going to blow up on me. Okay, but at least I can still do it for a population of for a sample size of 25. Okay, do I have an opinion on the let me do it myself. I'll do it myself up here, and we'll compare our answer. Equals, what did I have here? What was it again? It was 38. Okay. Uh, 7.6. Okay, I got a standard error for serum cholesterol for zombies of 7.6. Right? Okay, next question was calculating 95 and 99% confidence interval for mean cholesterol for the zombies. So my standard, okay, so X bar was 157, I think. 151.4. Okay, plus or minus 1.96 times my standard error, which is 7.6. So that's what I'm going to do for 99% confidence interval, for 99% confidence interval. 99% confidence interval, 151.4 plus or minus 2.58 times 7.6. Okay, so let's figure this stuff out. Can you guys work on it yourself? We'll compare our answers as we get done. 2.58 times 7.6 equals 19.6. Oops. Okay, 14.9. Okay, so 20 subtracted from this would be 131.4, 131.82. Let's see, 170. Okay, and on this one I get 15 subtracted from that would have been 135.4. And added to that would be 3 carried 1, 6, 666. Okay, tell you what I got. I got for 95% confidence interval, I got 135.5 through 166.3. You guys agree with me? Did I get it right?
I got 136. I got 136.5.
Oh, you're probably right. I can't, unless I have a calculator, I can't add anymore. 136.5? Yeah, I was trying to do it in my head. Okay, and what was 166.3, right?
Yeah.
Okay, I got that in right. And for my 99% confidence interval, I got 131.8. You may have heard me mumbling under my breath. Well, if I subtract 20 and then add back 0.4. Okay, 131.8 and 170. You guys agree with me on that? 171. I didn't even get that right. Oh, you're right. You're right. You're absolutely right. It's 171. Oh, man. Okay, how'd you guys do at home? I got a little bit of a lag on here. I don't think I'm getting them as quickly as Professor Waldron is. Okay, standard error. 7.6 is right. Yep. Okay, good. Okie doke. And I got one last problem for you guys to play with. Okay, based on a careful study of Night of the Living Dead and other zombie movies, it appears that zombies are, do you notice that they're mostly male, right? Not that many female. Male, and they seem to be college graduates. There's one right now. He was in a Hunter program. I remember him as a student when he was still living. He's still wearing his cap and gown. Okay, predominantly male graduate students. The proportion of males college graduates in the general population of living in the United States is known to be 0.48. There's a little bit more females than there are among the living. Of course, males, there's more dead males than, we don't live as long, so there's more dead males than there are. Population proportion of males is larger that are dead. Okay, a random sample of 100 zombies from Halloween weekend zombie movie marathons. 58 of this sample out of 100 were male college graduates. What is the 95% confidence interval for the true proportion of male zombies in all such movies? Okay, so what's P cap equal to? What is the proportion that, first of all, we don't know what P is, right? We don't know the true proportion of male zombies in the zombie population, right? So what we do know is that we took a sample size of 100, right? We took a sample size of 100, and we found that P cap is equal to 0.58. 58% of the zombies were male. Now we want to find our confidence interval for that. Okay, so first thing, I'm sorry. Oh no, 0.48 was the population. I'm sorry, you're right. The proportion that, you're absolutely right. Okay.
I thought PCAP was 0.58, but you said we don't know the population proportion.
No, that's the population of living males. I'm asking you for the confidence interval for the population of zombies. Male. So the proportion of males that are zombies is 0.5 in our sample is 0.58. So P cap is 0.58. We don't know P. We don't know P zombie, PZ. I'll call that. There's a special symbol for that, PZ. In the you'll find that in the literature, PZ, right? True proportion of zombies in the population. So we don't know what that is, but we know P cap from our sample of 100 zombies is 58% of them were male. Okay, so what is our standard error going to be? Standard error is going to be equal to the square root of P times 1 minus P, but the closest we can get to it is 0.58 times 1 minus P, 0.42. Now, before I go any further, there is a rule that we have to follow here where we're dealing with the standard error of a proportion. Remember I said to you, the only reason I can get away with doing this for a proportion or even for a continuous variable is because I have a certain sample size. N, I have to have a large sample. Same thing is true here. My sample size has to be greater than 30, just like before. But there's a special rule here. Now remember that I could have a situation where where P is equal to a small percentage, and our sample size may turn out that the people that the male zombies represent only 5 people, and the non-male zombies represent 25 people. It adds up to 30, sample size of 30, but we have an extra rule. Each side of that proportion has to be at least 15, right? So if I have a sample size of 100, how many male zombies do I have? I have 58. How many non-male zombies do I have? I have 42. I'm reluctant to call them female because they're dead. Okay, so it's 0.42. So I satisfy that rule where each side of the sample, each side of that proportion has to be at least 15. Got it? Make sense? In other words, if I had a proportion of 95 out of 100 zombies, I wouldn't be able to calculate my standard error because one side of that would be too small a sample size. It would be only 5 non-male zombies. Okay? So divided by n. Okay, standard error is equal to, and I'm going to divide, that's 100 down there. That's my sample size. Okay, so let's find out what our standard error is. Is equal to, clear, 0.58 times 0.42 divided by 100. Okay, divided by, take the square root of that, and my, interestingly enough, is very similar to the proportion we had before, is about 5%. My standard error is roughly 5%. I'm going to call it 0.05. I'm just going to round that off to just speed things up for tonight. Okay, so now, what is my confidence, 95% confidence interval going to be? Well, it's going to be equal to P cap plus or minus 1.96 times my standard error, which is 0.05. Okay, which is P cap, which it was 0.58, plus or minus 1.96 times 0.05 is 2 is 0.092. Sound right? Okay, I think that's right. Okay, so roughly my population proportion of zombies is going to be roughly between 0.672 and 0.4. Don't make me do this by hand. You know, you're embarrassing me now. 0.48 plus 0.488, I think. Right? So I'm 95% sure, based on our sample, that the true proportion of male zombies in these movies is between roughly 49 and 67%. Okay, I don't know. I can't watch every movie. There's 1,000 of them now. They're everywhere, right? I hope I didn't gross you guys out with this, because I know some people come from cultures where this is a little kind of, they take this stuff seriously. Huh? What? You don't have to round it all if you don't want to. You don't have to round it all. I get these questions all the time about rounding. I would try and make a reasonable judgment. In other words, I wouldn't report this as 0.4888392. It's not practical, right? So 0.488 is 48.8%. That seems like a reasonable rounding way to round to me. Now, technically, you round based on the number of significant digits that you have. For instance, I only gave you the proportion to 2 digits, 58.58. So you really can't even be more accurate than a third digit, right? So you could round to 2 significant digits if you wanted to, or maybe 3 if you were being generous. Yes?
Sorry, can we go back to that relationship between n greater than 30, because I just want to make sure.
Yeah, like for instance, let me give you another example. If I were to take a sample of a population of a population in nursing homes, I randomly it's a very large nursing home. They have thousands of people in it, and I take a sample of size 100, and I find 10% of the population is diabetic. That, in other words, I find out of 100 people, I find 10 diabetics. So how many diabetics do I have? 10. How many non-diabetics do I have? 90. Can I use that to estimate my standard error? No, because each side has to be 15 or greater, right? Even though the total sample size is bigger than 30, each side, successes and failures, diabetics, non-diabetics, each side has to have at least 15 people in it.
Because the other side, the diabetic only has 10, basically.
Only has 10, exactly. So it's too small a sample size. If that were really true, if I had taken a sample size of, if it were the same, if I just by luck got the right proportion and it really was 10%, if I had taken a sample size of 200, that would have meant 20 diabetics and 180 non-diabetics. I would have been golden. I could just go ahead and do my calculation. Okay, makes sense? All right, let's call it a night. Okay, and be careful going home. Right. Okay, good night, guys.
Thank you.
Yes.
This one, so I kept this as a 0.04.
Yeah, that's better. I just did it because I wanted to speed up. Yes. Like I said, you saw me doing something I tell you not to do. Don't round until you complete the calculation. At the very end, decide how you're going to round. Because then what happens if you multiply it by something or square it, you increase the error. Right? Especially since you have calculators. I'm doing a lot of this by hand to keep up with you. So, that's why I'm kind of cheating a little bit on it. Good night, guys. Good night, Eddie. Good night, Emily.